but I'm excited. 130 is really too much in Physics 101. We did it this semester because it was unexpected. We've never had that many. We had 50 in the calculus based. It's just we had a huge class come through that was a combination of different majors. All right, you have a hand up? Okay, what's the question? From the tutor assignment? The one that's due tonight?
Yeah, it has something to do with calculating flow rate in liters per second, and I was hoping that would learn how to convert.
Yes, okay, so with that, gosh, does this come up on the exam? It might. To understand sort of the conversions between liters and cubic meters, so your basic conversion is that 1 cubic centimeter, that's a cc, right? Cubic centimeter, that's equal to 1 milliliter. So for example, if I want to, what was the conversion, William?
It shows liters per second at a language of 1.6 liters.
2 liters per second, and so we want to keep
2 meters per second.
2 what?
Meters.
Meters? Where do the liters come in?
For the answer. I'm just trying to
Okay. Yeah, so what you would do there, I don't know what number that is, but you have 2 meters. What you have to do is you calculate what is the flow rate in cubic meters per second, right? Which is going to be a speed times the cross-sectional area. And then you want to convert that into liters per second. And to do that, well, you have to convert it first to cubic centimeters. So I would say there are 100 centimeters in a meter, and that has to be cubed. And then I have to convert that to liters, because I know that this is the same as a milliliter. So there are 1,000 milliliters in 1 liter. And then I also have to cube that. So the conversion is not trivial. You just have to think it through. But it's all going back to this concept, or this idea that a cubic centimeter, a cc, is the same as a milliliter. And then when you get your answer for that problem, what problem number was that? Number 11. You get your answer in cubic meters per second by multiplying the area and the speed. Then you can convert that then to liters per second. And these units would all cancel out and give you liters per second. Oh, and I'm sorry. No, you do not cube this. You do not cube it, okay? Because a milliliter is a cubic centimeter. Not on the test. You're not going to have to do that sort of conversion on the test, but it is important to do. Okay. What else? Yeah.
I'm not sure if this is going to be on the test, and if it's not, you don't really have to worry about it. But for when something is partially submerged.
Yeah, sure. So when something's partially submerged, so like we did in class today, really the only tricky part about this is you just don't take the whole volume. That you really just need to know what is the volume that is submerged. And so often, like in the OpenStax, there was a question that would give you the water line. What is the depth of the water line? And so instead of calculating the full volume of that thing, you would just calculate the submerged volume.
So just how would you do it? Like, let's say it's 10 meters. How would you set the problem up to find that?
I don't understand. What's 10 meters?
It's submerged 10 meters. Because, like, for the question, it says the water line is 1 meter.
Mm-hmm.
And that's the only thing I'm not sure how to set up the problem when we're given that.
I don't understand the problem. I'm sorry. I just don't understand the question. You have the question?
Number for
Oh, yeah. So this is the number 7. So the boat is 4 meters long and 2 meters wide. What is the mass of the boat? Do y'all know the question I'm talking about? I just skipped over half of it. I was reading it inside my head to myself, but not to you. But it gives the dimensions of the boat. It says that this is 1 meter, and then otherwise it's 4 by 2 meters. So it's 4 by 2 by 1 that's submerged. Now,
So width is 2 meters?
yeah, it's 4 by 2 meters. And the buoyant force, in this case, has to equal to the weight. So that's how we set it up, is that we say the buoyant force is equal to the weight. Right? And it's asking, what is the mass of the boat? Well, the buoyant force is rho times V times G, right? That's buoyant force, the density of the water, times the volume, this volume, which is length times width times height, 4 times 2 times 1, times G, and then that has to equal the weight of the boat, and then you solve for the weight of the boat. Did I get you in the right direction?
Yeah.
Yeah, and that's a good test question, sure. You need to know Archimedes Principle. There are a couple problems regarding Archimedes Principle. In fact, every little topic, there's so many little topics on this test, there's a couple of problems, except for torques. Now with torques, there's a string of like 5 or 6 questions regarding torques. We can do an example of that. We've done them in class, but we'll do it here too. Okay? Any other particular questions? Go away.
I'm referring back to 11, so what would be the key numbers to recognize?
I don't want to get bogged down in that question too much because those conversions are not really important for the test, but we can talk about it later if you like. Okay? All right, what else? You want to do one of those torque problems? Yeah, so look, we've done one of these, but you got 5 or 6 questions that are based on this topic alone, so it's a pretty big part of the test. So let's just step through one. Let's say that we start with a disk. Honestly, it's not going to be a disk on the test. It'll be some other shape, but it'll be a shape that we've dealt with. We've dealt with cylinders and bars and spheres, and we've dealt with discrete particles. So I have discrete particles all rotating around an axis. And no matter what the shape is, the thing that you want to ask yourself is, what is the moment of inertia? Well, for a disk, that's a cylinder, the moment of inertia is 1/2 mr squared. That's from my equation sheet, right? I have that table with the moments of inertia on it, and it lists for a cylinder that my moment of inertia is 1/2 mr squared. Let me show you. Y'all know what I'm talking about, right? Here it is. So on that equation sheet, which you need to know pretty well, from this table right here. So for a cylinder, it's right here, this 1/2 mr squared. So let's say that I would give you a few forces. I would say there's a force here. Let's say that this force is 20 newtons. Say I'll do a force here. Let's say that it's, 30 degrees, and that the force is 10 newtons. And the distance, the axis of rotation, the radius of this disk is going to be 2 meters, and my mass is 4 kilograms. And I would ask you a series of questions. The first question would be, what is the net torque? And you'll have a couple questions like that, where I give you different shapes and I ask you, what is the net torque? And the net torque is, you want to identify the forces that are applying torques. In this case, both forces are applying torques. The one on the left, this 20 Newton force, is applying a positive torque. Yeah, it's counterclockwise. And this one is doing a negative torque because it's clockwise. So to find the net torque, let's say torque 1 minus torque 2. It's just FR sine theta for all of those. So 20 times 2 times sine of 90, which is 1, minus 10 times 2 times sine of 30, which is a half. And so that's 40 minus 10, so 30 Newton meters. I could just ask you what is the net torque, and that could be a problem. Although I'm not sure if I do. Now, the next step, after you find the net torque, is you need to find the angular acceleration. And I might have a question, and in fact, I think I do have a question where I just ask you, I give you a shape with some forces, and I ask you, what is the angular acceleration? And since I know from Newton's second law that torque is equal to I alpha, right, that's our F equals ma for rotation, that alpha is equal to torque divided by the moment of inertia. So in this case, we don't know the moment of inertia just yet, so I need to figure out what that is. So it's 1/2 mr squared. That's 1/2 of 4 kilograms times 2 meters squared. It's 4, that's 8. So 30 Newton meters divided by 8 kilogram meters squared. That's 15 over 4, 7 over 2. That's 3.5 radians per second squared. So that would be the angular acceleration. And then further I could say, let's say after 3 seconds, what is the angular velocity? Or something like that. And we've worked problems like that. So say after 3 seconds, what is omega equal to? I would say omega equals omega naught plus alpha t. Omega naught, we would say is 0. It would say it's initially at rest. Alpha is 3.5. T would be 3 seconds. And so that's 9, 10 and a half, 11 radians per second. That would be a string of a couple of problems. Probably a problem where I ask you what the torque is, the net torque, and then another problem where I ask you what is the angular velocity. Or I could ask you here the angular displacement, and you'd use that other equation. So just expect that. You'll see a string of questions about the middle of the test, all right, where you have to answer those. Y'all can do that? You better, okay, because it's going to be on there for sure. And don't forget, too, that if I give you an object, sometimes, like we did one like this in class, to have a bar like this, is rotating, that I can have forces that don't exert any torque. For example, if I have a force like that, no torque. Or if I have a force like that, no torque. This one, because the angle is 180 and sine of 180 is 0. And this one, because r is equal to 0. It is at a distance of 0 from the axis of rotation. Okay, dokie? Y'all good on that? You might also have to do energy things. Let me, like I could also ask you, not what is omega, but what is the kinetic, rotational kinetic energy. Look, you had a question like this one on the OpenStax. I think the most recent one that we did, not the one due tonight, but the one that we did a week or so ago, where you had the hockey puck. Remember the hockey puck question? And you had to find the total kinetic energy. You will have a question like that on the test, but it's going to be a little bit different. I was about to say harder, but then I was trying to think of a better word than harder.
So no, it's yes, it is harder. Hey, you said how many?
We have to find the kinetic energy, the total kinetic energy. We have to find the kinetic energy for the puck spinning and its motion.
Right.
Would tires just rolling? Would that be?
That's what I'm about to show you.
Oh.
Yeah. So so it'll be not a hockey puck. It might not be a tire, but these ideas will still hold true. But imagine that you have a tire, right, that has a linear velocity. No, I don't want to put it right there. I'm just going to say that the velocity is equal to, I don't know, 2 meters per second. And I tell you the radius of this tire is 1 meter. It's a big tire. And I tell you the mass is 3 kilograms. And then I want to know what is the total kinetic energy. Okay, and just like the hockey puck question, you say 1/2 I omega squared, because it's rotating, right? Plus, it has this additional translational energy, 1/2 mv squared. Now, I know m and v, that's easy, right? And some of you might just stop and just do this, but that wouldn't be the right answer, but, you know, it'll be an option. But that tire has additional energy that's not just its translational energy, because it's also rotating, just like the hockey puck. So I also need to find out what is I and what is omega. But I and omega aren't immediately given in that. I'll need to calculate them. So for I go to my equation sheet. What is a tire? It's a hoop, right? Yeah, it's basically a hoop. So it's mr squared So my I for this would be 3 kilograms times 1 meter squared. And so that's equal to 3 kilogram meters squared. And then my omega, I also need to find, oh goodness, what is omega? Oh, it's going to be V divided by R. Remember how we related those quantities? V is equal to omega R, S is equal to theta R, and A is equal to alpha R. I just multiply the rotational quantity by the radius. So omega is V over R. That's going to be 2 divided by 1. 2 meters per second over 1 meter. So that's 2 radians per second. And then once I get that, it's easy enough for me to just plug in those values. And then that'll give me the total kinetic energy. Okay? That'll be a question on the test, so don't freak out. I want you to understand that there are quantities that are not given, but you can find them. What else? What was I talking about? I think that was all. You want to look through some old tests, or do y'all have additional questions? Look, we can also look through some of the OpenStax questions. I'll just scroll through this one. There's the one, a rotating disc. You have one like that. You probably have one like these where you're just sort of, you know, balancing torques like you did in lab with the rulers on the axis of rotations. The mouth thing, I don't know. It was just the words were not.
The mouth was just weird.
The words weren't. I didn't like the words. You're gonna have kinematic stuff like this.
What's the SI unit for kinetic energy?
Joules. Yeah.
Oh, can you go up?
Again?
Can you do that?
Yeah. So I can't show you the whole question. What was it asking for?
Yeah, that's like, how far away is the?
Oh, I see. The kid on the left is 26 kilograms. Yeah, so you'll have one. I'm going to do one not these numbers, but with some simpler numbers, okay? It's a lever, right? Where I have something that's like this. I have one kid here, say another adult over here, and let's say that the adult is 70 kilograms, the kid is 35 kilograms, and let's say that this distance is 1 meter, and I want to know what is this distance. That's the question basically, right?
It kind of like asked that, but it added another mass and another, like it said that the point was like farther away. And
Oh, it moved the pivot?
Yeah, it added more.
Okay. Well, let's do this one right quick. So I would say this force on the left is 350 newtons times 1 meter has to equal 700 newtons times x. And I would solve for x. And x is equal then to a half a meter. But if you move the pivot point, it doesn't matter. You just have different numbers. Or even if you have like additional people, like let's say instead we have another person over here. How would that change the problem? Let's say they're both 70 kilograms. I would add them. I'm just finding the net torque. Say that this distance was a half a meter. I would say 350 newtons times 1 meter plus 350 newtons times a half a meter is equal to 700 newtons times x. And I would solve that for x. I don't know what that is right off, but, huh? Are you serious? Are you guessing? Anyway, you can solve for x. All right? Is that sort of what the problem was doing? I don't remember exactly. And does that help? But look, you're going to have some I hope those are simple. Those should be quick and easy. The seesaw type problems where you're finding the force of the difference in axis rotation. Right, let's look back at some of these others. You'll have kinematics stuff, something like this. Make sure that you can use those kinematics equations. They might be even two-step kinematics problems, like not just simple plugging in the numbers, but you have to find the time or something along those lines. You'll have to relate your rotational to your translational quantities, like in number 6. This is another net torque, or this is actually finding the angular velocity. You'll need to understand how to rank moments of inertia. You know how to do that?
Yeah. Look for them, I believe you look for the ones that have most mass on them, then
Yeah, not just the most mass, because all the objects will
How
have the
far they are
same
away.
mass, how far they are from the moment of inertia. And we're all okay with that? Yeah.
Farther it is.
So, say for example, you've probably seen this question, there's one in an old test, but that has several different examples with different shapes, and you will see one like this, it'll just be different shapes. So you have two identical shapes. One of them rotates about this axis, and one of them rotates about this axis. Which one has the bigger moment of inertia? The one on the left or right? On the left. Because the one on the left, the mass, I have all this mass out here at a really big distance from the axis of rotation. But on the one on the right, not that much mass from the axis of rotation. I have most of the mass is up close to the axis of rotation. And then if I do another, what's another I could do? Oh, I could go along this axis, and then I could do another one where I go along this axis. You should recognize that these two are identical, right? They're just, I just switched it, they're like, flipped it. So those two have the same moment of inertia, and both of them have a moment of inertia that's smaller than this one, but bigger than this one. Look back, I have several different examples over the past several years of trying to rank the moments of inertia given the same object but different axes of rotation. You will have one like that where you have to rank the moments of inertia. Tell me.
So for the seesaw, or an equation like the seesaw, so there won't be a given mass of the seesaw itself, like.
I can give you the mass of the seesaw. In that case, if I give you the mass, we okay with this? Okay to move on from this? We'll be on there. No surprises. Should be able to rank those moments of inertia. Yeah, I could give you the mass of the seesaw. Usually, if it's rotating about at the center of mass, it doesn't matter. So if this is at the center of mass right here, the weight of the seesaw doesn't affect the torques. However, we did do a problem in class where we had to figure out the normal force. And to do the normal force, you say the sum of the forces equals to 0. You sort of had to do this with that jaw problem to find the force on the jaw, on the joint. And when you do the sum of the forces equals 0, you add up all the forces going up and all the forces going down, and they just have to be equal to one another. All the forces up have to equal all the forces going down.
I have the information for number 3 revealed, and then could you work it out? That's the information.
Yeah, I don't want to work that one in particular, but it's just the same as this one that I've just worked.
But it's without the mass of the seesaw itself.
Oh, but the mass of the seesaw doesn't affect the torques because the mass of the seesaw is at the pivot point. All right. Oh, you can show me your work later. We can talk about it. All right. What else you want to look through the old test or look through the OpenStax? Old test? Okay. I printed out a bunch here. All right. I have them. Look, there's one of those where you have to rank them. I have one like that, something similar to that. It'll be a different shape. Any particular questions you want to look at? Here's one. This is like the series of questions that you'll have. Number 7, 8. Was there another one? No, that one just had 2. I think I have 3 questions in this series of questions. You're going to have some. This is number 9. This one? Yeah.
Number 7 for the torque one. You just for 5 or for the 5 newtons, you multiply it times 2 in the video or something like that. It might have been this test. Why'd you use the 2 and not the 1 and 3?
Because sorry.
Oh no, it must not have been this one. Because if I look at,
It was something similar to that, where you use the whole door instead of the radius.
it might have been if it was rotating at this point. Then that might have been the case. Now, if I'm actually doing one where you have to find the acceleration, I wouldn't do that because if you look at your equation sheet, the equation sheet only has a thin rod rotating about the middle, not a thin rod rotating about the end. Those are two different things. But on this one, no torque, no torque. So it's only the 10 Newton force that provides a torque. So the torque is 10 Newton meters clockwise. Y'all follow that? You see that? Listen, as I told you in class today, a number of the questions that if you're really quick and you really know this, you're not going to even have to write anything. But you'll be able to look at it and you'll say, oh, not that answer, not that answer, not that answer. So it has to be this answer.
So what would it be if it was rotating around like the end of the door?
If it was rotating, say, around this end,
Or the other end?
yeah, if it was rotating around this end, I would have a torque here, and it would be 10 times 1 meter, because that's that distance. It's always the distance from where the force is applied to the axis of rotation. And then it's going to be sine, it's actually sine of 50. Don't worry about that. I'm always going to give you, oh wait, no, it's not. It's sine of 40. Sorry. It'll always be the angle that I give you. That would be the torque if it was rotating about this axis. This would be the only force that would cause a torque. It would be counterclockwise. It's going in this direction. And this force would not provide any torque at all. Courtney?
Can we do number 10?
Yes. Lauren, are we okay with this? Okay. Yeah, so ranking torques. On this, the forces, these three forces are all the same, and this force is big. And these three all have a moment arm, and this one has twice that moment arm. So you can probably, what you want to do on these ranking problems, especially when you have ones that are equal, is ask yourself which ones are equal. And you can tell, if you look at these, that these two are equal. Because remember, torque is Fr? One of them has twice the force, but half the moment arm, and the other has half the force, but twice the moment arm. So these two are equal, A and D. So that allows me to get rid of, oh, that gets to get rid of all of them. So the answer has to be A.
Easiest one.
Yeah, and then A is equal to D, and that's, both of those are bigger than B and bigger than C and then bigger than B. I know that C is bigger than B because these have the same moment arm and the same force, but this one, not all of the force goes into the torque because it has an angle, right? It's like you're only getting a component of this force that's causing a torque, the Y component. That sine theta term becomes relevant. Okay? All right. Light ranking problems are good for it to sort of make your mind go and think about them. All right, let's move down and look at some of these others. I have a seminar at 3, so unfortunately we can't go past 3. Bernoulli's principle, you'll see that. You're going to see Pascal's principle. You'll see the same picture. It'll just be different numbers, okay? Make sure you can do this. Remember the pressure 1 is equal to pressure 2. Have to measure pressures. As I told y'all in class today, you will see one that's very similar to the grouper problem that you had on OpenStax that's due tonight. I think we did that in class today. Y'all okay with it? It's just a little bit tricky because you don't have the volume of the fish, and you have to find the volume, and you might not know immediately that you, one, need the volume, or that you know how to get the volume. But because of that relationship, rho is equal to m over v. If you know rho and m, you can find v. And the other tricky part on those problems is keeping your different rows separated. And then also recognizing that you have the rows in that chart, that you have the densities in that chart on the equation sheet. So they're not difficult, those problems, but there's just a lot of different information for you to assimilate. And then that makes it a little difficult, especially when you're in the throes of a test. Huh?
Nothing, I'm just,
No, what'd you say?
I'm just saying difficult, that's what you're looking for, you sound.
I don't like to use that word because, you know, if you know it, it's not difficult. And many of you do know it. And, or if you're just learning it, you know, if you haven't really mastered it yet, then you can do it, but it's just going to be a little more difficult. And if you haven't really been practicing along the way and haven't really been keeping up, then it's going to be difficult. Okay? Let's see. You will not have any, if you see things on the test that have to do with moles or temperatures or any of that business, you will not have any of that. Okay? We had a similar problem, this bus with a 2,000 kilogram flywheel. That was the 90% problem on that previous test. This is ranking. This is moment of inertia. Remember when you have two objects that come together, the moment of inertia is the sum of the inertias for those two objects. So for example here, you'll see this, where you have two objects that come together, and you have to tell me what is the total inertia. What is this? This is a disk, so 1/2 mr squared, and then it has a point mass at the edge, so just mr squared for the point mass. All right? Somebody raised their hand? Who was that? Yeah, John. No temperature. So that's chapter 10. We didn't get chapter 10 at all. So if you see anything that has ideal gas law, moles, linear expansion, temperature, you see any temperatures at all, that's going to say I'm not doing that. Okay? I'm not too worried about getting chapter 10. It's like chemistry. Y'all have that in chemistry.
Yeah, I know. Yeah, I know. Temperature and calories and stuff. That was
boring.
I was gonna say that was like the worst part of all of chemistry, and I hated all of chemistry.
No, chemistry is really cool, but
yeah, it's fun to yeah. You're not the one who has to do all the math.
All right, we haven't really looked at conservation of angular momentum, but absolutely you'll see some like that. This is like number 5 or number 6, the combined angular momentum, or when you have objects that change their angular momentum, like the figure skater who throws her arms out and gives herself a bigger moment of inertia, that makes her speed decrease, her angular speed decrease. All right, what else, y'all? Yeah, but you will see it on the test. So remember, we did a couple examples in class. I appreciate you asking that. We did a couple examples in class. For example, the Ferris wheel. Remember the Ferris wheel? Say a Ferris wheel, you can be at the top or at the bottom. In both cases, I have a weight acting downward and a normal force acting upward. Normal force, weight. However, in these different cases, my centripetal acceleration, AR, or we call it AC, I think, is in different directions. And so the way that I write Newton's second law is going to be different. Fn minus Fw equals m times AC, which is v squared over r. But this needs to be negative because AC is negative. It's downward. It's sort of like the elevator problems. Remember the elevator problems we did a couple of tests ago? It depended if the elevator is going up or down because it changed the direction of the acceleration. And over here, it looks very similar. Fn minus Fw equals positive mv squared over r. And so when I'm solving for Fn, which is usually what we're doing, Fn is going to equal to the sum of Fw and that And here it's going to be the difference of FW. I have a bigger normal force on the bottom part. It's like it's pushing me down into the chair more, so I have a bigger normal force. We did another problem similar to this. It's the same. I mean, the math is still the same. Is when you're going over hills in a car, and you know the top of the hill is like being at the top of the Ferris wheel, and the bottom of the hill is like being at the bottom of the Ferris wheel. Now, probably I would give you not V, but I would give you omega. And so omega, I don't know, what does a Ferris wheel do? Like a revolution a minute, or maybe 2 revolutions every minute? Omega, if I gave you omega, there are a couple things you could do. You could replace this with m omega squared r. Remember, that's also the centripetal acceleration. Or you could just say, well, V is equal to omega r. Either one would be okay. But remember, never go wrong with SI units, that this needs to be in radians per second. And y'all know how to convert. You will have some just conversion problems, and I hope those are gimme problems for you, that everybody gets those right. Yeah, converting revolutions, degrees, or radians back and forth.
And radians to reps per minute would be just multiply 2 pi over 60.
Yeah, remember your conversion factors are 1 revolution is 360 degrees is 2 pi radians. So 2 revolutions per minute, for example,
Equals 360 degrees.
equals 1 revolution, 360 degrees, and then you also take care of the minutes. 1 minute, 60 seconds, 12 radians per second. Yeah.
The reason is that one of the OpenStax problems specifically convert 3 involving rotation. I got the first answer right, radians per second, but I got reps per minute wrong.
Number 3? That was on this assignment, wasn't it?
Yep.
Oh no, that's a different one.
Rotation.
The rotation one. Say when you buy your when you buy your subscription to Tutor, does it last a year or a semester? Do you have to pay again next semester?
I think it's a year.
It's a year, so you're all
I
paid.
know I've had like paid.
I was thinking about changing just to doing it just on Moodle, but if y'all already paid up, we'll just keep it. OpenStax, like, I like it. But I know that a lot of the answers are online. And so y'all don't get a whole lot out of it if you just get the answer online. Like, I understand.
And it actually gives the explanation about why you did it wrong.
I can never find it online.
I wish it would tell us, like, we could submit it, like, at that point, and then it tell us if we got it wrong, and explain how, like, through, like it did for math itself.
Yeah.
Kind of like for peers.
Yeah, they're working on that. All right. I'm sorry. What was the question here?
It was number 3.
What's
I
that?
didn't say like fully how you got it wrong.
Yeah.
I wish it would have like a
The problem was
full
number
workout.
I understand. Yeah. What was the question here?
Number 3.
Number 3?
Yeah.
Well, you probably moved it to revolutions per second, and they were asking for revolutions per minute.
Multiply the answer, multiplied it by 2 pi over 60 in the calculator. In parentheses.
No, that's not right. 76.2 radians per second.
Times 2 pi over 60.
In we need to go to minutes. In 1 minute, there are 60 seconds. And then we're going to revolutions. In 1 revolution, there are 2 pi radians. So you need to multiply it by 60 over 2 pi or 30 over pi. Okay? Make sure you can do those conversions. They come up several times in the test. There are 1 or 2 problems that are just straight up conversion, convert this to such and such.
It's 7,000.
Okay. But there are also sort of conversions that you have to do within problems. Never go wrong on SI units. It's not always required, like with kinematics and momentum problems, not required for you to change to SI units. Newton's laws problems, SI, yes, you must always go to SI for those. I try not to make it tricky, like I don't want to trick you into doing it wrong, but sometimes you have to convert with this problem. Alright? What are your plans for the weekend?
Study, study, study,
Isn't
and
that
study.
suck for Monday tests? I hate them. Do you have any other questions?
Yeah, exactly. What do we-
Any other burning questions? I think I got everything off my chest that I wanted to do. Alright, make sure you come up and see me before you go. Shoot.
This is my fault.
So,